So, welcome to week number 11. Just let me quickly check that my mic is loud enough. We can get more. Good. So again, welcome to week number 11 of Type Systems for Correctness and Security. And as usual, we start with the exercise. This time it was exercise number 9 on object orientation. So in this exercise sheet, we had exercises regarding object calculi on the lambda calculus and on featherweight Java. It's more of a lengthy exercise sheet compared to the last ones, so we might take some more time for that as well. Let's see. But let's dive right into that. So first exercise was objects on the lambda calculus, and the idea was to write a subclass of this reset counter class from slide 17 with an additional method deck that subtracts 1 from the current value stored in the counter. Good. So the first thing that we'll do is we'll set up a type for the deck counter. So that is 911. We set up a type for the deck counter, and that is this one. And the record for that is that we have a get, goes from unit to nut, unsurprisingly an inc, an increment operator, or increment method in this case, that goes from unit to unit, a reset function that goes from unit to unit, and now the new one comes in, the deck function that goes from unit to unit. No? And interestingly, on the solution sheet there is a semicolon here where there must be actually a right parenthesis here. Well, okay. Good. So the idea is to write a subclass, so we have to write a class primitive for that. So that is deck counter class, and of course it takes a representation. We did not change the representation here, so we can just take the general counter representation that we used before, and then we have the super reference. So let super be a reset counter class. So the super class that was forced here in the exercise is reset counter class, and we take the same representation, of course, and then we'll fill the record, and get is of course just an alias for super.get, and inc is an alias for super.get inc, because we don't need to do anything else. And we have the reset, which is of course super.reset. And last but not least, we have the new implementation for the deck method, which is of course lambda wildcard unit, and then an assignment to r.x. That's the implementation that we now need. We need the predecessor of the dereferenced value of rx, and that is our new deck counter class. No? And that's actually it. Nothing more needed, necessary to do that. Okay, fair enough. That was not that difficult to get you started. It's just a bit lengthy to write. Now the second task here was define a subclass of backup counter class, which was on slide 19, with two new methods, reset2 and backup2, controlling a second backup register, and this register should be completely separate from the one added by backup counter class. So calling reset should restore the counter to its value at the time of the last call to backup, as it does now, and calling reset2 should restore the counter to its value at the time of the last call to backup 2. Oh, so a little bit more complicated backup functionality. Good. How does that work? Let me just quickly scroll you up a bit. Does that work? Is that hold? Okay, it seems to be going. Okay, so 912. Okay, so the first thing is, of course, we need to find the type for this class, and this is backup counter 2, which is of course get from unit to unit. Get from unit to nut, and inc from unit to unit, and reset, typed as unit to unit, and then backup as in the original type, unit to unit, and then the new methods called reset2 and backup2, which are typed exactly the same. Here, reset2 unit to unit, and backup2 unit to unit. Okay, so this is your type, and of course the thing is we need to extend the representation type a little bit here, because we have a second backup to consider. So backup counter rep 2 would now be x, a reference to a natural number as in the original, b, a reference to a natural number as in the original, and of course then b2, which is a reference to a natural number. So far, so unsurprising. So next thing is the class implementation. So backup counter class 2 takes, of course, the new representation type that we just defined, which is a subtype of the original one, because we just added one. Remember records and subtyping. So backup counter rep, 2. And then we have again the super reference, which is of course the backup counter class. And then taking R, and we can pass R to backup counter class because it takes the super type, and the subtype is more precise, so it disregards just B2, but in general you can use these two fields, and we can use the B2 in our implementation here, and that's what we want. And let's get right to it. So we have the get, which is set just super.get, and we have inc, which is just super.inc. No, we don't need that. And we have backup, which is super.backup, and reset, which is super.reset. So we don't change these, but we now have different implementations. So we have backup 2, which is a new function, wildcard lambda function, because we don't need the input because it's unit anyway. And then we set B2 here to the dereferenced value in Rx. And then of course we need reset to, which is also a lambda function with a wildcard, which sets Rx to the dereferenced value of the second backup B2. And there you go. And this is the implementation for that. So that was rather straightforward. As we've seen in the lecture, it's just an application of everything that we've learned so far to object orientation. So this is all just constructed out of things we already had in the lambda calculus before. Nothing fancy indeed. Good. Even though we're quite alone today, are there any questions for the first part of the exercise? And if you can just give me a no, that would also be fine, so I know there's a reaction. Great. There are like a few bits and pieces that you can interchange, so there is no one solution here as well, but something that's compatible. Good. So moving on to featherweight Java. So the exercise here is by analogy of the stop rule in our lambda calculus with subtyping. One might expect to see a rule stating that object is a supertype of every class. Why don't we need it in the rules for the for featherweight Java on slide 37 and the following? So why is that the case? Well, the thing is, in featherweight Java, if you remember, everything had an extends clause. Everything at least extended from object itself. So we explicitly have this subtyping relationship expressed in the syntax itself. So we don't need an explicit stop rule that states that object is the supertype of every class, since we have it in the syntax anyway. The other thing is, and since these clauses are not allowed to be cyclic, the chain of extends clauses from every class must eventually end with object. And if you just visualize that a little bit, so we have let's say we have a class A and we have a class B and we have a class C. And all of these, so this is some kind of pseudo UML, or it is actually UML. So we have a class object, and these things already extend from object directly. And then let's say we have a class D that extends from B, which extends from object, and transitively we have this connection. As we have no cyclic connections, I could not just go back and attach B to D or C to D and so on. I could now like say, okay, it's not object, and C down, put it down here. That would be fine. But for instance, let's make a more complex cycle. Let's say we have E also, and let's say we have an, oops, no, this direction, F down here, and this F then has a G, and E now, let's say we don't have that anymore, and E now extends from G. We couldn't have those. This is a cyclic thing, and then everything must come back to object, because if there's no other connection, it's object. So it naturally forms a tree. So you don't need this explicit stop rule for once. Good. Moving on to the next thing. So conditional expressions. So conditional expression in Java is a term of the form T1 question mark T2 colon T3. So the things that you can do in C, you can also do these. So these shorthand things for an if. So if we would extend featherweight Java with the construct, we would need a typing rule. And now the idea is to formulate a typing rule. And the idea is that T2 and T3 still might be of different types and need to be combined in a manner that allows maximum expressivity in your language. So should be straightforward to us to do that. So let's just formulate first what we want to have. So we have T1 and then T2 else T3. And we need to type that. Let's keep that open for now. And what do we already know for our rule? Well, under the same assumptions, T1 must be Boolean. Otherwise, this would not work. So we can force that. And let's say, so the exercise said that T2 and T3 might be of a different type. So let's give them a different type to get started. So that this to be like T2 and this to be T3. So what's the overall type of this thing? Well, it's of course the join, as we need to join these types together to find the least common supertype for these two things, and then we would have the thing that comes out of the if. So beware, there is a join here, and then we are safe. Now we can type this expression. Okay, moving faster than I thought. That's not a problem. We have enough in the lecture today to keep us busy. So, as we have time, any questions for the 9.2 one? So I don't think so either. So let's move on. So the next exercise was a bit more lengthy. It won't fit here on this screen part. I can just simply make it fit. Then you wouldn't see my solution. So just to quickly walk through the exercise here. So open recursion with self. So our current definition of open recursion through self actually has a problem. So the way we defined the instrumented counter class, it cannot be used to build instances. If you write new instance counter in the usual way, in this way with the fix operator, and then attempt to create an instance by applying it to unit, the evaluator will diverge. And why this is the case, we will now learn. Because we now consider the sequence of evaluation steps, processing the term above, first applied to new instrument counter unit to unit, which yields the following. Good. I will scroll this up a bit and move the cam a little bit up so we have everything we need anymore. Good. Nice that is so flexible. Good. So we have now this little term, and the idea is now to continue to evaluate the term above, of course you want to stop at some point, because if it diverges you will never stop otherwise. So you should find a point where you actually have shown that it diverges, and the evaluation rules are on week 2, slide 70, pretty helpful. So let's just walk through this a little bit, and I will follow the same pattern as in the solution document, if someone wants to read along. So what do we have here? We have two record cells, X and A, that are packaged into a record. And let's call this record IVARs, just to save space. We're on 931. Good. Let's just call this IVARs to just save a little bit of space, so we don't need to write everything in there. So this is equal to X ref 1 A ref 0. Good. So the term that we have here when we unrolled the let for a bit is then fix, and then the call to instrumented counter class, and then of course this placeholder IVARs. Good. So this is the thing. So, and when we pass IVARs to this instrumented counter class, this is the application that we have. So what unrolls then? Well, it's fix. I don't know if it's one step or two steps, so just write it like this, so it works all the time. So you have the self-reference, so instrumented counter class, and then the expression is let super equals set counter class, and then of course IVARs again, and then self in, and then it's the methods. I'm not going to repeat all the methods here that are implemented. It's just a placeholder for these things in this way. So up here, I methods are defined as the methods of instrumented counter. Good. So all of this in this form that we have right now with the parentheses closing the thing, let's call all of that F in such a placeholder format. It's just syntactic things just for brevity, so we can have this thing here. Not the entire thing, so just this parenthesis here to here. So this is now F. So what we have here when we rewrite it, this is equal now, is fix of F. So now we can apply this efix beta. Efix beta, which then unfolds, and by substituting this for self in the body, so this basically is then substituted for self in the body of F. This is what the efix beta does. So the resulting thing that you would have, because this is kind of the thing you apply then fix with self and so on to this, is then let super equal set counter class. Again, the variables, the ivars, and then self is then substituted by fix F again. I don't need these parentheses, but they're in there now. And then the methods, of course, to complete the let. And then we have that. And now we have we can reduce the application of set counter class and ivars, because this is a method, this is a function, and this is the parameter. And this results in this. We can now have that. Now we have set counter class. And then these so-called S methods. These are the methods from set counter class. So we have made that a little bit abbreviated here. And then, of course, again, fix F. And then, of course, in I methods. So now we can again apply this to that. So this is a method, and it takes self, takes a set counter. We can use that, and we can reduce this to something in there, which is then until the letter is reduced to a value, means that we can have this. So what we then what we can do, we cannot reduce this application because this is not a value yet. See there? So for application, we need these both things to be a value. This is already a value. This is fine. Functions are values. But this is not yet. Now we can apply efix beta to that. So the only choice here is that we reduce this fix F again. And then let's do that. What we then have is self set counter s methods, and then we'll reduce that and we get let super be equal to set counter class, and then ivars again, and then of course again fix f in I methods. We're carrying this along as we go. And of course all of this here is also in I methods. This is the outer thing that we had before, and this is the inner thing that we now reduced from applying efix beta. Good. And now as the argument of the outer lambda abstraction is still not the value, we must continue to work on evaluating the inner one. So we perform the evaluation then again as to set counter class of ivars, which then results in the following. It's a lot to write, and I have to scroll you again. There we go. Let super be, and then we evaluate this part here. So the outer part stays the same. So lambda self set counter s methods. Yeah, is that right? Yeah. And then let super be now the unrolled version. So lambda self set counter s methods. One is enough. Oh, this is the S. Okay. And then of course applying this to fix f again in I methods. Whoops. Methods, and of course again in I methods. There's an S missing here. Good. And now we created an inner application, so this all would have become very familiar to you, because this is basically in the inner thing what we did in the outer, and then we have the same situation again that we need to unroll fix f again, and then we would diverge. So just as before, this inner application cannot be reduced until its argument fix f has been fully evaluated. So this thing here. So when we do that again, we will again unroll the whole thing and would again have the efix beta applied again, and then again unroll the inner part now of this thing here, and then come to the same thing, and so on. And so on and so on. So at this point, you now have shown that this thing diverges and would never terminate. And that's the idea here. Just to show in 2 steps that you would like loop again and again and again in the inner thing, and you would never come to any conclusion until you exhaust any kind of resources you might have. Good. Second part of that exercise was how we can actually fix it. So how is that worded here? The intuition here is that the argument to the fix operator is using its own argument self too early. And we can protect the reference to self in the instrumented counter class by inserting a dummy lambda abstraction. And the idea here is that an arbitrary expression t can be turned into a function if you just put it inside the body of a wildcard function like this. And this is called a thunk. This is very common in functional programming. Whenever you need some delayed evaluation, you typically turn things into a thunk. It is kind of from a behavior point, it is kind of more or less the same, but evaluation then later on comes into thing. You know? Evaluation is postponed, one might say. And this now gives us means, as I've written in the solution, that we pass around here without fearing that it may be evaluated too soon, as it was in this case. And as we can say, we don't need to change any rules now, but the idea is that we change now the implementation of set counter class and instrumented counter class to protect self. And the thing is, it will change their types. So let's inspect this for a second. So what do we need to do to do that? 932. Is that in view? Yes, but I will scroll a bit like this so I have more space. Good. So the idea is now to change the implementation of set counter class. What we still have is, of course, the representation type, counter rep. And what we still have is, of course, the self-reference, which is now a little bit different. Remember, self was used to be a set counter, but now as we've thunked the whole thing, it's unit to set counter, of course. And then we have the thunk. And in the body of that, we have get lambda unit r.x. So this is the old implementation of unit again. Set I as natural number, and the update to the reference Rx is now I, of course, because we use the set. And now we have something that uses self, the inc. And now we can actually force evaluation of self and use it in this way. We use self unit dot set parentheses open successor of self unit dot get, and of course we need to provide a unit for that because get takes a unit, and then close the parentheses and we're good. As you can see, like, using self has become a little bit more different because we need to specifically unroll the self-reference here when we actually need it and use it, but we are then sure that it is just unrolled at this particular point when we actually use it and not just way before. So what changed in the type of the whole thing? So set counter class is now, of course, counter rep to unit to set counter. This is the self-reference type here. And this goes to unit, and this goes to set counter again. This is the format that we now have. We also need to change the constructor a bit. So new set counter is now a function, wildcard function, going from unit Oops, and then we have the body of that, which is let representation be x reference to 1, so initialized with 1 in fix set counter class R, and this provided with a unit because we need the counter rep and we need the unit to get things started, to get to the next counter class, which is self. So we need that to evaluate first. And the type of this does not change because the outcome of all of this is there a unit too much on my type? No, not really. The outcome of all of this is this unit to set counter. No? And there we go. Then now we fixed it because we've put it into a thunk up here. So just to quickly remind you, we call that a thunk. Yeah. And we have now the explicit dereferencing of that, or not dereferencing, but explicit access to that at this particular point. Yeah. So this is delayed evaluation is the effect that we have. Oh. That's the nice thing. Good. Any questions for 9.3? Or any remarks, anything that you find particularly interesting here that I haven't discussed so far here in this exercise session? Okay, does not seem to be the case, which is great. Good, so we start in about 10 minutes with the lecture, so that would be 10:57-ish, round about that. At least 10 minutes of a break. So see you in a second.
Comme s'il était fou, même toutes les rats sautaient sans trou. Venez tous, chaque soirée joue dans la rougette des zombies dans son chapeau. Dab dab, bidi 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 ba. douches, manus, barbini, doucement, une sentimentale, venez tous, ces soirées jeux dans la rue, les rois douches, manouche. techo. Por el agua y por el fuego. Por tu espalda cuando duermes, la tarántula te puede picar. Cuidado, desde el suelo vigila la tarántula. Ve con cuidado, desde el techo vigila la tarántula. La tarántula vigila. Desde el suelo, desde el techo. La tarántula vigila. Desde el mar y desde el cielo. La tarántula vigila. Desde dentro de tu mente, la tarántula te puede picar. Ponte la inyección. Si te pica la tarántula, no hay otra solución. Si te pica la tarántula, aprende la lección. La tarántula te puede picar.
Okay. Good, welcome back. So, our lecture today is one of the last lectures of this course, as you might have already guessed. And today we're first going to talk about higher order type systems. So higher order systems enable us to do much more with the type system than we had before. And you would see that we now reciprocally use the rules that we have to build up even more things on a higher level to express even complex problems with type systems. And first, kind of the observation that we used type abbreviations for a long time now. So, for instance, we used boolfun to describe a function going from Boolean to Boolean. So we don't have to write the whole term for that. So these are just abbreviations, just syntactic substitutions that we can introduce at any time. For instance, for a pair, we used down the line actually this part. So in the last lecture, I talked about polymorphic typing, and this is one instance of that. So let's have a first look at that. So that says, okay, for all x, we have as the type a function going from y to z to x and then to x. This is just another fancy way of writing a pair constructor for x and y. So what you get is a pair of x and y, in a sense. I need not to dive into polymorphy at this particular point, but just so you know, these are just the same thing on the left denote the same thing on the right side. So yeah, basically. So just that you know, for now we used abbreviations for even longer things that we did not want to introduce at that particular point. We also have very special type constructors, as we call them. We used array-t in at least one example, and we used ref-t a lot to construct references. So these, we use them in a way that they are constructors, but they are rather functions on the type level. So ref-t basically takes a type and returns a reference type, as you can think of it. So these are functions on the type level. A type constructor is a function on the type level. And these type operators, these functions on the type level, so when we have them and when we introduce them to our language, that means we can introduce the concept of abstraction application in the lambda calculus also on the type level. So we can make computations that again result in types, not in terms, which is totally neat. And we will see why that is the case in the next couple of slides. However, in order to do that and to have type operators working really, really well, we need some rules for equivalence. We need to show that two types are actually equivalent in that means. Also, a new terminology, a piece of new terminology that I did not highlight on the slide is type term. So type terms, usually we have seen types as uniform things, but now as we can use abstraction application, we can write terms that reduce to types. And this is a so-called type term. And this is why we need to show equivalence, because on the trivial side, these type terms may not look the same, but may compute to the same thing. And what we also need is a higher level concept also for types of types, because there are different types that can be used with type operators and some cannot be used with others. And we also, when we have types of types, we need a well-formedness relation for type expressions. And this relationship is called kinding. So when we are on the basic level, we have terms, and then we have types, and on the top level now we have kinds introduced. And the way it works is a little bit like this. So let's first start with abstraction application. So the nice thing is, if we can introduce it here, we can reuse the same notation on the type level that we used on the term level. So let's say we have something that we call a uniform tuple. So something like a record tuple that consists of the same type, like bool bool in this case. Then we can use a lambda function here that takes a type and constructs a new type, which is then a record type, using this type variable. And then when I execute that uniform type bool, I get a type that is like, as the result of that application, I get a type that is a bool b bool as a record. We can also support things like currying. Here is a little bit of a different way of writing the same thing that we had before. So pair lambda y, lambda x, and the all quanta for x. gives us a pair for this. So we can use multiple arguments for that. That also means that we have used the informal convention of parametric abbreviations, so things like refbool, for instance, with a formal definition of type operators. So what we basically do is here we clean up our language a lot by defining what we mean when we write things like uniform tuple bool. We need to not to encode that into the actual syntax of the language. We can leave that open. Okay, let's talk about kinds for a thing. We need to have kind of well-formedness for type operators. Sometimes you cannot use type operators in the same way for the same types. And the way to do that is actually to introduce kinds, which is kind of a type of a type operator, if you feel, a type or a type. So the star. So kinds are typically expressed with stars and arrows. So it's just a syntactic way of doing that. So the star denotes the kind of proper types. So these are things like bool or function types like bool to bool. All the types that we've seen before, with the exception of any kind of type operator thing, is a proper type. So any type like bool, nut, int, string, whatever, is a proper type. And now we have this star, arrow, star kind, which is the kind of type operators. These kinds of type operators take proper types like bool and result into another proper type like function type bool to bool. So this is the way to denote type operators, the kind of type operators. That's star, arrow, star. And then you can construct multiple things with that. Star, arrow. It sounds a little bit silly to read it out loud, but that's the syntax that we have right here. These denote the kind of functions from proper types to type operators. So you have a proper type that gives you a type operator, which resolves a proper type to a proper type. That is, for instance, two argument operators are in that kind. So functions that take proper types to type operators. And if you have multiple functions, you can just chain these. If you have multiple arguments in your function, in your type operator, you can just chain these. And then you have denoted this kind of kind. However, your type operator again is then of a different kind, and so on. And then you have the parenthesized version. So parenthesis star, arrow star, parenthesis closed, arrow star denotes the kind of functions from type operators to proper types. So that's a function that takes a type operator and gives you a proper type. We will learn multiple examples for these in the future. And this is the last kind, is that we call a higher order type operator, because it takes a type operator and gives you a proper type. So just as an example, hopefully you will all participate in this little quiz. So what is the kind of this type? So you have pair that takes A, which is a proper type. Have a look at these two colons here that denote not the type, but the kind of the type. So colon is kind, just colon is type. So it takes an A, which is a proper type, and a B, which is a proper type, and gives you a parametric type in this case. So what do you think is the kind of this type? That's the point where you open the chat window and enter something. Maybe I show you the previous slide again to give you a sort of clue. So these are the kinds that we learned about. So we have the star, which is a proper type. We have the star to star, which is the type operator. And we have the star arrow, which is the a function from a proper type to a type operator. Or we have the other kind, which is the parenthesized version of star, and then arrow star outside of the parenthesis, which takes type operators to proper types. So when you have seen that, what kind of type, what is the type, the kind of this type? Okay, that takes a little bit too long. It's of course the star version of this, because it takes a proper type, which is A, and then gives you another type operator, which is lambda B, and then the rest of the body. And this type operator then gives you a proper type. It's a little bit hard because you're not used to seeing parametric types here. Because we didn't cover them in detail in this lecture, but however, there you kind of see how this fits together. So this is what type operators basically do and how they're kinded. And to do that, to include that, we need a little bit of a new syntax. That is the lambda calculus with kinding. I actually forgot the Greek letter to look up the Greek letter again, what that is, but it is the extended version of the lambda calculus. And the gray parts here are the new parts. So the white background parts, that's the thing you already know. And the most notable thing is on the right side, you now have kinds, which get you proper types, and then the kind of operators. So that's k arrow k, which means you can construct arbitrarily complex proper types, kinds from kinds of proper types and kinds of operators. And then you see you have in gamma, you have another addition operation. So gamma now hosts not only our expression types, so term variable binding, but also type variable bindings. So the kinds are also stored in gamma. So not to pass around a different context that may get out of sync here, you just use the same context for different things. And then most notably you have an extension to T, which means you now have type variables. As you have term variables, you now have type variables. You have operator abstractions, which is this lambda x colon k dot t, big T, yeah. And then you have type operators, which takes big T, which takes a big T and applies it to a big T. This just formalizes the intuition that we had before, so that we include everything into our language that we actually need to make this work. So as you can see, very little additions. So let's look a little bit how this works. So we need a few rules for kinding now, because this is the this is what gives us if a term is also not properly typed but also properly kinded. So in general, gamma t gamma turnstile t colon k is what we're looking for here. And as you've seen with the lambda calculus, this should be rather familiar. So you have also a kt var, which is basically the kinding rule for type variables. That's why it's called tvar now. And this basically tells us if the kind association is in the relationship of gamma, you can type a type variable as that kind. Yeah, or you can kind that type variable as that kind. Typing. And then you have abstractions, of course, which just formalizes abstractions. This is the same thing as the t-abs rule, basically, but just rewritten to kinding. Yeah? Also, the k-ab rule, which is just a rewritten form of the t-ab rule. And you have a k-error rule as well, which gives you the type kinding for function types. And as we've seen, function types are typed as proper types, and this is how they're constructed here in the type system, in the kinding of things. Good. As I've teased on in the start, we need some rules for equivalence. So we need type equivalence, and a type is always equivalent to itself. This is the Q reflexive rule here. Yeah. And equivalence is always symmetric. So if S is equal to T, exactly then when T is also equal to S. Of course, you can interchange them, and then you can see that things are equal in both directions. And also type equivalence, as you can see, is also transitive. So you can, if you have a U in between that is equal to S and is also equal to T, then S is also equal to T. This is quite naturally the case, but it needs to be defined. And then you have the Q error rule, which basically tells you that equivalence is also invariant, as you can see here. So if S1 is equal to T1 and S2 is equal to T2, then S1 to S2 and T1 to T2 is also equivalent. So if all the parts of an arrow type of a function type are equal, then the arrow types are also considered to be equal, which is very nice and composable and can easily be shown in a proof. Okay, and then we have the more complex definitions. That's the equivalence rule for abstractions. And that means if the body type of an abstraction is the same type, of a type abstraction here is the same type, and the input parameters are the same, of the same kind, then they're considered equivalent. Good. Application, also the same thing as arrow types. So if you apply a type S1 to S, if you take S2 as the parameter to S1, and S1 equals T1 and S2 equals T2, then of course the application of T1 to T2 is also considered to be equivalent. So equivalence also is stable over application. And then of course we need some rule for application to abstractions. So the substitution case. So when we have a type operator on the left side, and then type parameter that is applied to, and x that is equal to the substituted form. That means that the types before the application are equal to the types after the application. So we in a way we preserve kinds also, we preserve type equivalence also through things. This is in a way a fancy way of writing type preservation, if you will. Okay, onwards. How does we change typing? Just a bit. We need to force that when we're now on the term level, actually, here in the lambda calculus. As you can see, this is the t-abs rule that we're talking about. However, as we've now added higher order types like type operators and higher order operators, to our language, we need to make sure that when we do term application, we only do this with proper types. So for the abstraction here, it is necessary that T1 must be of a proper type kind. This is absolutely necessary for the T1. For the parameter to be of the simple type kind. So the input parameter. This rule. Yeah. Okay. Sorry. Yeah. Genau. Yeah. I was actually telling the truth. So the parameter needs to be of the simple type. And as you can see, like the abstractions on the right side, like the function and the what is with the body type? Yes, I was just coming to that. The body type can be anything. So you can have lambda terms that give you type operators as the result. That is valid, and we will use this in a second, so bear with me. No, it does not need to be proper. Just the input parameter needs to be a proper type. That's the only requirement that we make here. But bear with me. We will apply this stuff in a second for something very, very nice, and then you will see that the output parameter, even of a lambda abstraction, does not need to be of a proper type. Good. Application is unchanged, but we force a new rule for equality. So when we have an equal type S, we can type the same thing as T or S, given that T is of a proper type kind, and that means that S must be equal to that proper type kind. So you can have something of a higher kind. However, it needs to be equal to a proper type. So it eventually needs to evaluate to that. Good. That's the first part of this lecture. That's based on chapter 29 of the book. This is just about higher order types and type kinding. And now we move on to a different topic that is related to the ones that we just had, which is basically an application of the one we had. And this is called dependent types. And dependent types are quite key to understand modern type systems and how they work, including the Scala type system, which we will talk about in the next lecture. So one of my first slides that I show you is this little slide, what type systems cannot do. So this was an example in C where the type system actually was not able to see that we were accessing the array beyond the defined scope. And so you had like this array with 3 elements, and reading past the limits not checked statically. And the interesting thing is, like in C, it returns whatever it is in the next memory block, and in Java you have a runtime check that gives you a runtime exception when that happens. You already know about this. I was not actually quite honest with you with that slide, so type system can actually fix that. Only Java and C don't do this statically. So we will now see a type system where you can actually formulate this, and where you can actually add static checks to your program that will actually make this much more safe. Looking back at what we just learned, so type operators. Type operators are type-valued functions because their return value is not a term but a type. So we call them type-valued functions. And dependent types are also type values functions, but they use terms as their input. And this is why in our application rule, only the input type needs to be a proper type. Also, dependent types not take types as the parameters, but terms, but result into types again. Good. Let's develop something for arrays. So we've seen this problem with arrays, so let's find something that actually works. Yeah. So we've seen some representations for arrays before. So we had this nut array thing that is basically a reference from a natural number to a natural number. So a reference to a function. Yeah. As we've seen, this is kind of the definition what we have in C when we translate it to our kinds of languages. This is roughly the same. And as in C, we have the same problem that we have no control over the length of the array using this definition. It could be any arbitrary length. It could be long, it could be short, it could be 3, it could be 3000. We wouldn't know. Yeah. We will try now with the more general definition of the type itself. And not to confuse things, we call now this a vector. And we use now kinding to describe the type that we would like to construct. So a vector is kinded as a type operator going from natural numbers to any type. It maps a natural number to a type, to a proper type. So the intuition here is that the natural number is the length of the vector. So we include the length of the vector in its type. And to make use of this type, we need a way to construct it. And this is the way to do this. I will walk you through this syntax in a second. Yeah. So init is typed as a vector, which is itself a type valued function or a so-called type family. Yeah. And in order to construct this, we need a so-called dependent product type. Yeah. It's a so-called pi type. So the left part of that function type here is this pi n dot nut with a body of data. Now we will soon learn what this is about. So init is now applied to a natural number n, and a value of data, and the result is a type of vector n. So data is basically initial data, and n is the length of the vector we want to construct. And of course, as we're in the type universe, this is not the data itself. This is a fixed type for the element of the vector. So whenever we have something like an array, all of the elements are of the same type, of course. And we need some data type to describe that. And this is what we use data here for. So as you see, we have a function that takes a natural number, which we call init, that takes a natural number n and constructs a type, an array type from data to vector n. So it uses the parameter on the right side of the function type. And let's look at product types for a second. So product types is a generalization of the arrow type that we've learned so far in the simply typed lambda calculus. It is the type of function which maps elements s of type s to elements of x substituted with s in t. So we can now substitute elements in a type. This is so-called product type. And the result of such a function with a pi type, a product type, can vary according to the supplied arguments. So this is pretty neat. We now have types that depend on terms. And as we apply them, there need to be values. So in a sense, we have types that are depending on values. And that's why we call them dependent types, by the way. Let's look at more type constructors for the array or the vector example here. So we have this cons operator, which is basically functional language talk for add something to a vector. And cons here takes a natural number n, an element of type data, and a vector of length n. So that's the second argument. So n, data, and vector n, and results in a new vector n plus 1. So let's use that for a second. Cons 5, so vector of 5 of x and v is a vector of 6 if x is of type data and v is of type vector 5. So now we have added an operation to our type family that helps us add things to a vector, but then results in a new type of that family. Because later on we would like to check, is it a vector 5 or is it a vector 6 that we want to use here? Or is it at least a vector 6? We can also do things like that. Now we can add things to our vector. We can also have operations like this, which help us to find lower bounds. So first, of course, cannot be applied to an empty vector. So if n is 0, then we don't want to. If n is 0, we cannot supply a first element. And this is an insane level of type safety for operations that we have not achieved so far. So for a one-dimensional array, that would be that cannot be done, because we don't know if the vector is empty. We always need something like a guard condition that tells us if the vector is empty. Even if we have something like not a natural number to data to array, we wouldn't have that, because in array we wouldn't have any kind of length argument that we could check in the type parameter type of such a function. So I first said that this is a generalization of the array, the arrow type. So why is that the case? Let's define that a little bit more closer. So we have this arrow type. Let's say we have a function going from S to type T. And this is nothing else than a pi type taking an x of type S as the input argument and outputting something of type T, where x does not appear free in T. Again, we are here on the type level. Don't think in sense of terms. Think in sense of types. So what do we need to do to get the same types? So an arrow type S to T is the same as a pi type that takes x of type S as an argument and returns T when x does not appear free in T. So this is independently of whatever value we put into, we always get T in here. If pi type x takes a natural number and is a natural number, that would be natural number to natural number, because x does not appear in nut. It's not nut x, it's just nut. It's just natural numbers. So the nice thing is we can unify all of this now, and we can use product types synonymously for function types if we wanted to. You know? The nice thing is, if we formulate it in this way, it gives us higher flexibility without losing anything in the original lambda calculus. Before we do that, before we unify that, let's look at a little bit more complex uses. So whenever you programmed in C, you would probably come to a function called like sprintf. So that takes kind of a format, string, and a list of arguments that must correspond to this to the format string. And let's try to do this in with dependent types now, because we actually can do that. Yeah. So for this, we need the format string to be a little bit more formal. We need it to be in a form where we can actually like sequentially pass that. Yeah. So sprintf is now a pi-typed function that takes a format and results in a function going from data f to string. Again, we're on the type level. We're not on the individual evaluation level. We're just trying to find a typing for our sprintf usage. And now let's look at data for a second. So data of an empty format would be unit. So things of an empty format string would mean that you would not use any data. So it can be applied to the empty to an empty list of arguments, or it should only be applied to an empty list of arguments actually. And this is why the type is unit. So in the upper general definition, data f would be unit. So a function would result then in a function going from unit to string, which is exactly what we want. Because we used the format already in the type definition. We do not need to use it as an input argument. And then let's say we have a case where f is actually a %d, which takes which is in sprintf terminology decimal number. And then a couple of more format things. That's like this ::cs basically tells us, okay, there is more. Yeah, there's some consecutive parts in this format string. That takes us that it has that now gives us that we have product types here that take a natural number, and then again we recursively now go through the remaining format and require data of that remaining format. As you can see, we can now parse this whole string along and come up to a definition of an input parameter. So that can be like, if you have that again %d, it's natural number, and then if it's then the empty part, it's unit. So it's natural number, unit. So that means that you can apply this sprintf function typed like this to 2 arguments, and only 2, not 1, not 3. Of course, you can do this with other types. So in the format, if you have a string, if you have a %s, then on the right side you force a string. And if you have a C, just a regular character, you just disregard and don't use it in the type. You only use it then in the sprintf function. Okay. So that's a very neat thing. So you now can encode things in the type system that depend on actual input values, which is really, really neat. Of course, if this is a runtime input value, then this makes it a runtime type check as well. You need to be aware of that. However, you can use the same type checker statically as or dynamically as you would like, because it's the same ruling. So this is very appealing, and so let's construct a type system with dependent types. And as this is rather like comparatively new development here, you would find multiple ways to construct a type system with dependent types. Next week, when we talk about Scala's type system, or a Scala 3's type system to be exact, we would learn another way. Right now, we're talking about the Lambda LF framework, which is the lambda calculus, based on the lambda calculus and the so-called Edinburgh logical framework. This is a logical framework defined by researchers from Edinburgh, as you see, quite natural. And this thing uses product types as we present them here. However, out there, if you look for that topic, you would find other formalizations using different representations. I will shortly discuss them afterwards, not to confuse you too much. Because the syntax sometimes is a little bit different. You have to map the constructs a little bit in your head. But that's what research is all about. We struggle so long as we find a uniform and harmonized way of expressing these things, or whenever someone something prevails, as with substitution, which we've seen before. So the syntax of symbols actually changes a little bit. So how is lambda LF constructed? And this is actually the complete syntax. It's nothing more. It's the terms you know quite well. This is just the lambda calculus. T is much more like that lambda. What's the Greek letter that we had like in the previous part of the lecture? I think is that the rho? I don't know. You can look it up if you're interested. But the thing that we had with higher order type system looks pretty similar. However, you still have type, or so-called family variables. Yeah. But instead of these type operators that you had in there, is that you had just dependent product types. Yeah. And the application here is type family applications. You can take any T and apply a term to it. Yeah. Kinding works also very easily. You either have proper types, or you have so-called type families, which is pi types, nothing more than pi types, yeah? Which return a kind and not a type, as you can see here. Yeah? Rather neat. So you can also apply it to type families as well. Yeah, and gamma looks like the same thing as we had before. So you can add term types, term variable bindings to gamma, and you can also to type variable bindings to gamma. This is the same as we had before. New thing is type variables can describe also families. They don't need to be proper types. They can also be families of types. And kinds categorize into proper types and type families. A little bit different than we had before. Yeah, and contexts are just used for typing and finding. Finding? That should be kinding. Wow, I found a typo. I will correct this. Good. So, by the way, typing. How does this work now in lambda LF? You have 4 rules now. You need this little last rule, which I will explain in a second. But what did change? Type variables can only be terms can only be of proper types. No? This is a little bit different. Abstractions also give us the same thing as we've discussed with the previous part of the lecture. So the input part, the input parameter of such a type family, of such a pi type, must be a proper type, or the output doesn't need to be. Application works in the same way as you know it from the lambda calculus itself. However, T1 is now a pi type. And why is that the case? Because we have shown that we can show equivalence to we can show that we can express arrow types in pi types with x not appearing in T. And this makes the same thing. And this makes that we can substitute the x below with T2 in T if that's needed. Pretty neat. And now the fourth rule. The fourth rule now gives us is basically the equivalence rule. That tells us, okay, if we can type a term as T, and if we find an equivalent type T prime, which is also proper type, because variables, as you see up front, needs to be proper types, then we can also type T as this T prime. However, in order to be a proper type, it needs to be evaluated down to a proper type. So you cannot take the type operator and do that, but you can show equivalence and then you can do that. Okay, so term variables can only be typed as proper types. This is a little bit different than before. However, abstractions now use the pi types, so the generalization, and the same way as we had it before. An application substitutes the operands of the pi type. So on the type level, we now have application, and there we have the substitution by the operand of the pi type. This type conversion rule allows us to exchange the types with one that is considered equivalent. Nothing more, nothing less. How does kinding work? Kinding basically works in the same way as you've just learned it in the previous section, but let's walk you through this a little bit more. Is there animations? No. Okay, so for the kvar not. So the kvar usually works like this. So you have type variables, and if the reference appears in gamma, and also the kind of the type is in gamma. Now you have also kinds in gamma, because you can have multiple arbitrary kinds in there. Then you can type a type variable as you can kind that type variable as that particular kind K. It's very tempting to always say type, but I mean kinding. Good. The kinding for pi types is that they are proper types, in a sense, if the input parameter is of a proper type, and under the assumption that the input parameter is T1 and gamma, the output type is also a proper type, but only then. Application also on the kind level now, so we can construct certain kinds using pi types with kinds instead of types, and then we can substitute x with t in that type kind. And then we have kind conversion, so whenever we find that there is an equivalent kind, we can also use this equivalent kind k prime to kind something in that sense. So terms used as operands of pi types need to be proper types. This is what this rule forces. And you can also apply pi types on the kinding level. Keep that in mind. And you can always replace kinds with equivalent kinds. Because you now have operators, applications running for kinds, we also need equivalents for that as well. So what is then a well-formed kind? So we have this WF star property for well-formedness of the entire gamma thing. Well-formedness of, so any proper type is already well-formed. But now, as we have application in the game, we also need to make sure that all the applications also produce kinds that are also well-kinded, well-formed kinds. And so whenever we have a pi type that is like x of type t, and then in the body has k, and t is a proper type, then under the assumptions of gamma and that x is of type t, then the k must also be well-kinded, and then the whole pi type is kinded, and this grounds it to proper kinds. So proper types, so the star kind, and then you can construct arbitrary complex kinds out of this one star, basically. The same that we did rather limited in the way that we did it before is now much more generalized. And as you can see, it comes with two rules, which is kind of, I think, couldn't be done any more elegant. So what does it say? So all proper types are well-formed, and the pi type is a well-formed kind if the operand type is a proper type and the resulting type is well-kinded under the assumption that x is of type t. As you might have substitutions. Okay. One thing that we didn't touch here is now equivalence. So the main question in this type systems is when two types should be considered equivalent. So in a type system with dependent types, so a very natural notion is to equate types that differ only in their term component when those term components themselves should be considered equal. So when you have static parts of a type, you don't need to consider them. This is basically what this says. You can only look at the difference in their term component. When they only differ in their term component, then you need to look at the term component, otherwise you're fine. You already know your answer. So the thing we need to show now is term equality. This is a bit difficult, so let's postpone that for a second. And let's first establish kind and type equality, because that's the much more easier task here, and formalize the intuition that we just formed. So kind equivalence in lambda LF works like this. Do I have? No, I didn't. So I have to explain this all myself. Good. So kind equivalence here for pi types works like this. So if T1 and T2 are considered to be equal and to be proper typed, so the star kind, and if under the assumptions of gamma and that x is of type T1, which is equivalent to type T2, remember, then we can assume that kind 1 is equivalent to kind 2. And now what is kind 2? That is coming from the conclusion. That means that if we have a pi type that has T1 as their input type, and if we have a pi type that has T2 as their input type on the right side, and we have K1 and K2 on as the body of the pi type, we can consider them equivalent if and only if their input types are considered to be equivalent, and of course proper, as we need them to be proper, and the output types of K1, the output kinds of K1 and K2 must also be considered equivalent. Then the whole thing is equivalent. So it's like a build-up thing. Okay, and then the thing we need is like you have like the proper kind, the star kind, and then you can build up of all of these things using pi types. What you need actually here is reflexivity, symmetry, and transitivity. I'm not going into this because at this point you should be so used to them that this comes very natural. So equivalence is reflexive, symmetric, and transitive. This should be pretty much obvious right now. Type equivalence, by the way, is also reflexive, symmetric, and transitive. Not going into detail there, but talking about type equivalence, that means if we have a pi type that takes an argument of S1 and has a body of S2, and if that should be considered equal to a dependent type that is like a pi type that is taking T1, has a body of T2, and this is of proper kind, the whole output of that, then S1, this is the case when S1 is equal to T1, so the input types must be equivalent and must be proper types, and also under the assumption of the input type of T1, which is equivalent to S1, so you can substitute whatever comes naturally in your proof, then S2 is also considered to be, and S2 is considered to be equal to T2, and they are also proper kinds, and this is then gives you type equivalence according for pi types. Yeah. And then you must also show this for replications, so before and after the substitution of the variable in the type kind. No, in the type K. Why is this a single colon? This is weird. Okay. Okay. Yeah, and as I said, it's reflexive, symmetric, and transitive. Okay, let's look what that means, because term equivalence is quite complex. We postponed that, and now let's do that. And let's first look at type family applications with the beta redex, so beta reducible expression. So you have a type, so T, with an input parameter of a lambda function, lambda x of type S and dot x, so some identity function in a sense, for some S, and on the for some Z, applied to some Z, and that should be equal to T of Z. Yeah, that comes quite natural. If you apply the identity function to Z, what's the result? It's Z, and that should be equal to TZ. Yeah. So this is a beta reducible expression. So this is something that you can reduce in its current form, because we do not need to know what Z is actually to do that. We can just rewrite this whole term and then come to the same thing that is syntactically the same, and then find that it should be equivalent. But let's consider something that is not a beta redex, but beta equivalent lambda terms. And they should be equal. So this should also be true. So vector of 3 plus 4 should be a vector of 7. So let's say you have a vector of 3 and you added a vector of 4, and the result would be a vector of 3 plus 4. Not a 7, not in the evaluated form, but in the unevaluated form, because currently we don't do that. Yeah? And then you have a function that takes a vector of 7. What do? You need to show that 3 plus 4 is actually equal to 7. Yeah, to us that comes very natural, but for an execution engine or for a type checker, this says, okay, function 3 plus 4 is not equal to, is of course not equal to the value of 7. It is equivalent, but it's not equal. So that means that we might need to evaluate arbitrary complex evaluations, and even might require proof in the general case. So let's say we have a vector of f applied to x, and that should be equal to vector 7. Yeah. As you can see, this is Turing complete. This could compute anything and can take any length of computation. That's typically not something that we want in type systems. So we reduce the definitional equality. So we use definitional equality, which means we only consider obvious equality. So not any computations, but a subset. And namely, if you want to look that up, that's beta and eta equality in lambda terms. So there are a few definitions of equality in lambda terms, and that means that so they're like beta and eta equality means that this is only considered to be, yeah, you can think of it like obvious equality, like 3 plus 4. This is something that you can easily determine as such. If you have like a random number generator, this is not something you can easily easily think of. Or if you have like a bunch of functions that sometimes like diverge and sometimes come to a conclusion, this is also not something that we consider beta or eta equality. I'm trying not to go into much details here, not to overfill your head with this information. Just as the notions to look it up, it's beta and eta equality on lambda terms that we use in lambda LF. And that gives us a new rule, two new rules called Q beta and Q eta. Do I have? Yeah. So Q beta and Q eta rules are the only interesting rules here. The other ones we've seen already in one form or the other. So let's look at the beta rule first. So the beta rule tells us that when we have on the left side an unapplied function, so lambda x of type S and the body is t applied to S, then we can consider that equal to a substituted version where x is substituted with S in small t, but x is also substituted as S in big T, because we might have a pi type. Yeah? So equivalent to its substituted form. So if it's just substitution that we're missing, then this is fine. This gives us the case with the identity function, of course, because in the reduced form we just have z and this is equal. This is perfectly fine. Yeah. The eta thing is a little bit more complex. That says, okay, we have a lambda function, lambda x as t, with t applied to x. So in there we have another term, and this term, as you can see in the premise, is typed as a pi type. Yeah. So that can be anything from like a function or like a higher order function. No, we don't know that. And the other premise is that x is not in the free variables of t. This means that we actually have an arrow type and nothing more complex than that. And then we can consider t typed as that pi type as eta equivalent. So this leads us to the type equality. Okay. Just a few hints to what we can do with that. We can extend lambda LF and like take dependent sum types. This generalizes ordinary product types similar to the way dependent products generalize ordinary function types. So you can see you have the ordinary product type that you had before. So T1 product T2 that we had like in 1 or 2 lectures before, if x does not appear free in T1. This is the primitive type, but however you can have also dependent sum types here. Yeah. Another way that you can do what you can do now is you can construct the so-called calculus of construction, and this takes lambda LF and adds concepts for propositions and proofs. And if you remember in one of the first lectures, I talked about the Curry-Howard correspondence between proofs and so the world of mathematical proofs and the world of typing. And this is actually the binding. The calculus of constructions gives us that, and this is, I would say, one of the important basics for automatic proof checking also. we won't go much into detail. I'm just going to show you how easy it is if you already have lambda LF to actually do something like this, which takes like seems very like science fiction-y at that point. So what you need is universal quantification that we had before. This all is basically this all mathematical operator that you've seen before. And as new types, you also add propositions and families of a family of proofs. And the kinding for that is that propositions are kinded as propertypes, and proofs are then pi types that take in their body a propertype and as their input parameter a proposition. And typing uses then the all quantifier to bind it all together, and type equivalence defined as this unit. And this means that you can actually do mathematical proofs with propositions just using an execution engine for lambda LF to actually do what you want to do. So it's all pretty neat. This is then based on the Advanced Topics in Types and Programming Language book, chapter 2. If you want to read up a little bit more on that. However, any kind of like exercise questions will not go beyond the scope that we've heard in the lecture today. I think that's my last slide now. Yes, this is my last slide for today. We still have a couple of minutes for questions. So if you have questions for the first part or for the second part of the lecture, just let me know. Is a proper type something like a well-typed type? Yes, you can say that. You can say that. Any like also complex types are then well formed in that way. As kinds like elevate types to types one higher level up, we can also talk about well-formedness in that sense. Okay, so we're going to have an exercise about that. I'm going to reveal we're not going to have a lab about this. We're not going to implement dependent types. This goes a little bit beyond like a 2-week lab at the end of the semester, I'm afraid. But next week I'll talk a little bit about how the people in the Scala world actually elevated their type system to that levels, and hopefully in the Scala 3 version you can actually do most of the things we talked about today actually in the programming language itself. Then kind is like signature for that functions. Signature for that functions. Can you help me a little bit out with that question? I'm not sure that I understand what you mean with signature. I might just pull up a slide for that maybe. Oh yeah, in a way, that's true. Yeah, the kinding helps us. To define the input and output parameters of a type that is like a pi type. Yes. Okay, if there are no more questions, I'm closing this session a little bit earlier. So lab number 6 just came out, if I'm not mistaken. Should be. Yeah, that's today. Great. This goes for, again, 2 weeks. And then we have lab 7, if I hopefully finish that until in 2 weeks, but I'm most certain that is. I've just publicized the results for lab number 5, so you should be able to see your results right now. Always have a look that you're already auto-graded. I have 2 solutions. With one of them I already talked about this, why this does not compile on the grading server. I see another one here. I will look into these things manually, so no need to take any action for you. Only if you did not receive the full amount of points and you feel that you should have received the full amount of points, then let me know, and then we can talk about a little bit more why that is the case. But you see the details of the grading and where you got points detracted also in the results of the grader. So please be sure to check them for asking a question. I would also like to remind you that today at 2 I'm going to have like an open office hour, from every Wednesday right now on. Also, one simple reminder, soon we can start with the exams soon after the semester stopped. So if you want to tackle the oral exam early on, please register first. The way it works is you write one of these, you take one of these nice forms that we have on the computer science website, and send it to my secretary, and then she will arrange a date for the oral exam, which, as you might have guessed already, will probably take place over an online interview. So please make sure that we have software for that. We already prepared a bunch of things for that, so don't worry if you happen to have that not in that case. It would be beneficial if you have a camera. If you don't have a camera, please indicate that in your email. You of course need some kind of microphone to be able to talk to us. It's an oral exam that needs to work, and like a headset is very beneficial. You would have seen this in the last couple of weeks of remote working already, that a headset will also be very beneficial for that. Other than that, feel free to use any material in the course, but be reminded it's a 40-minute test, so don't expect to have time to look things up much in the exam. It's a conversation, and we have to keep the conversation going, because the expectation is that we fill the 40 minutes with the conversation and not you looking up things. So be prepared as to a standard oral exam in standard as well. Next week will be the last block of lectures. So after that we will only discuss the remaining exercises. There won't be any new content afterwards. As I mentioned several times already, next time will be talk about the type system of Scala, especially the ongoing change to Scala 3 that's been going on for a while now. and that's particularly rooted into the topic that we had today on dependent types. So be sure to check that you understand dependent types before watching the next lecture video. Good. Yeah, any more questions in then the office hours or later on in Panda, as you wish. Okay, thank you very much, and see you later if you like.